So, why don't we get started? So today we're going to continue on with this first segment of continuous distributions. And where we left off, well, first make sure you're keeping up with the reading. We will have written exam number 2 a week from today. I'm going to have it in class because it is a little bit easier to do that. And so that means it's probably going to be more on the conceptual side. I won't ask you to calculate things, but I will pose scenarios and ask you which distribution you'd use to best describe this scenario. Okay, a bunch of questions of that nature. Again, you're allowed one 8.5 by 11 sheet of paper for your notes, and it'll be scoped to the full class meeting period. Okay, so we left off, we're talking about probability, mass, and density. And let's jump right into uniform distribution. The uniform distribution is drawn between two parameters, A and B, that define the bounds of the uniform distribution. If we were to draw what the uniform distribution looks like, now this essentially corresponds to the situation where you have real valued quantities, but those real valued quantities, my knee brace is slipping. Excuse me. You have real valued quantities that are equiprobable. And so if you were to draw what this distribution looks like, you have along the horizontal axis all your values of x, and we have two parameters, a and b, that describe the uniform distribution. Along the vertical axis is our probability density. Now recall, it's a density if we're talking about real valued quantities. And then we have here the values of this probability for uniform is 0 up until the point where we get to a, and the probability is 1 over b minus a for all those values, bless you, in between a and b. And then all values of x that are greater than b, it goes back to 0. So this is what our uniform distribution looks like. It's a distribution where all of the uncountably infinitely many values between a and b on the real number line are equiprobable. Okay. Any questions about this? So it's fairly straightforward, and one of the things that we'll do is take a look at the sampling routines in MATLAB associated with the many distributions that we cover and their properties, and use that to do some modeling. Okay. All right. So these are, if you look at the total probability of the uniform distribution, right, that would just be the integral from minus infinity to plus infinity. So the integral from minus infinity, so here's minus infinity here, here's plus infinity here, from minus infinity to plus infinity, all the possible values of x, all uncountably, infinitely many of them, and we'd take the probability, which is 1 over b minus a dx. And so, of course, law of total probability says that this quantity is equal to 1. Okay, so that being said, when we look at this real number line along the horizontal axis, we notice that this distribution for all points from minus infinity to a, it's equal to 0. And likewise, this probability is 0 for all points from b to positive infinity. So we can rewrite this total probability, or this expression for total probability, by taking this and recasting it, taking into consideration piecewise all of the regions of our domain x on the real number line over which this is defined. And so we write then from minus infinity to a, we take that same probability density integrated dx, and then we add that to the result from a to b of our density 1 over b minus a dx, and then we add to that the remaining portion from b to positive infinity of 1 over b minus a dx. Okay, so we know from definition, if the height here is 0, i.e. the probability, the uniform, is 0 for all values of x less than a and all values of x greater than a, this term is just 0. Likewise, this last term is also 0. So all that remains is to compute this integral of the center portion, which corresponds to the area under the curve over here. Now, of course, you could do it visually or you could do it mathematically. It's the same result. If you do it visually, you'll notice, okay, this is a rectangle, and the length of the rectangle, this length, is equal to b minus a. So you multiply the length times the height here to get the area. The height is 1 over b minus a. 1 over b minus a times b minus a. You have the same quantity in the numerator and denominator, so that goes to 1. And our result here is 1, and we get a value of 1 for the total probability. So this is, in fact, a probability. If you wanted to do this using the integral, I'm going to erase this graph so I have a little bit more room on top. Well, what do we have? We have this integral. We have the integral from a to b of 1 over b minus a dx. Now, of course, this 1 over b minus a, it does not involve any x value, right? This is an integral for x goes from value a to value b. And so underneath this integral, for all intents and purposes, this 1 upon b minus a is a constant. So we can bring that out in front of the integral. We write 1 over b minus a times the integral from a to b of 1 times dx, right? Now, of course, the integral of 1 is just x squared, 1/2 x squared, right? So this becomes 1/2, 1 over b minus a, there's our constant. And we're now taking this definite integral and we're evaluating it using the indefinite integral. So for the indefinite integral, that would be 1/2, I'm sorry, no, not 1/2. X to the 0. It's just x, right? And we evaluate that for this x. We evaluate this expression at value b, and we subtract from that expression at value a. Okay. So now, if we take this integral, bless you, we have this 1 over b minus a. So we take this expression, we evaluate it at b. So that becomes 1 over b minus a, x evaluated at b, that's just b. And then we do it again, evaluating it at value a. That's 1 over b minus a, x evaluate a, call that a. So we get this expression, and then we collect the common factor, 1 over b minus a. So that becomes 1 over b minus a times b minus a. Okay, we have the same b minus a in the numerator and denominator. That goes to 1. So the value of this integral mathematically is 1, which also satisfies this law of total probability. Okay, any questions about this? Does that make sense? Okay, so now for our uniform distribution, and I again apologize for using the board. We had the pen for the tablet, was working Tuesday. I don't know why it's not working now. Let me just, since I'm stubborn, I'm gonna take a look and see if the sharing came up. Nope. Let's see if it found it. 335. So how I have things set up is you can't do the screen record from a tablet and display at the same time. So I use the laptop as an intermediary. And for some reason, to use the pen, you need the tablet. And for some reason, sometimes it blocks the share for the tablet to the laptop, which is what this air server thing is. But all right, okay, so let's just continue on and go from the board. I have some old video. I'll post that for the derivation stuff if anyone wants to take a look at that later. All right, so let's now turn our attention to the summary statistics for this uniform distribution. We have a value for the expectation for the uniform distribution is a plus b over 2. So let's go through what that expectation means. Now remember, for expectation, e of x is equal to, and because this is a continuous distribution, we're going to use the integral from minus infinity to plus infinity, and we're going to say x times the probability of x. Now, of course, we're going to substitute for what our P of X is for this uniform distribution. And we know for a fact that the uniform distribution is 0 anytime we are to the left or less than A or greater than B. So I'm just going to recast this integral for the uniform distribution as being the integral between A and B of X times P of X. Now, of course, for the probability P of X, we're going to substitute the density function F of X for our uniform distribution. So then we would write integral between A and B of X times 1 over B minus A, where this 1 over B minus A dx is our density function for the uniform. So let's do this expectation. And again, mathematically, we see this 1 over b minus a. And remember, for the integral, our index of integration or variable of integration is going to be x. That's why it's called dx. And this 1 over b minus a looks like a constant, so we can bring this out of in front of the integral, a factor, 1 over b minus a. And what we're left with is the integral from a to b of x dx. Okay, so by the rules of integration, we will compute this definite integral using the indefinite integral, and we're going to take the indefinite integral for this upper bound, and we're going to subtract from it the indefinite integral for this lower bound. So when we first do this indefinite integral, right, so we have 1 over b minus a quantity, that leading coefficient, and then for this x, we're going to get 1/2 x squared. Okay, and we're going to evaluate that at the b index and at the a index, and we're going to substitute the evaluation of this indefinite integral for x is b and for x is a. Okay, so if we do this, well, let's just kind of gather these coefficients here. I'm going to rewrite this as 1/2 and 1 over 2 times b minus a. So we just multiply the 1/2 with the 1 upon b minus a. And then we have our x squared, and we're going to evaluate that at b, the upper bound, and at a. Okay, and we'll subtract. So here we're going to take the evaluation of our indefinite integral for b, for x equals b, and then we're going to do the same thing for x equals a. Okay, so if we evaluate it at x equals b, we get our leading coefficient. That hasn't changed. I'm just going to talk about what happens to the x part. So we have 1 over 2 times b minus a, which is a common factor for each of these terms. And then for x equals b, we get b squared. And we get, for x equals a, we get a squared. So what we're left with here is 1 over 2 times b minus a. And then we also get b squared minus a squared quantity. Okay. So if we do that, this b squared minus a squared is the same as, let's see, let me write it up here. Let me erase up here. B squared minus a squared is the same as b minus a times b plus a. We can actually verify this. That's b squared minus ab plus ab, right? That goes to 0, plus minus a squared. Okay, that is exactly b squared minus a squared. Okay, so we can replace this b squared minus a squared with b minus a times b plus a. We have that in the numerator. And in the denominator, we have 2 times b minus a. Okay, well, we look and we see that we have a b minus a both in the numerator and the denominator. So that goes to 1. And we're left with b plus a quantity over 2, which is our expectation. Okay. Any questions about this? Does that make sense? Okay. All right. So now let's look at the variance. And for the variance, we're going to first, no questions? No? Okay. And again, I'll post some video. I have an old video of some of this to go through. Unfortunately, we don't have a pen, so it's a lot harder to do it like this. All right. So let's take a look at the variance. And for the variance, recall the variance equation that we had from before. Variance of some variable x is equal to expectation of that variable squared minus the mean, e of x, quantity squared. So we just got done computing what the mean was. It's a plus b over 2 for the uniform distribution. So if we take this part of the expression, the variance equation, that's a plus b over 2, let me write that a little bit better, quantity squared. Now if you square this quantity, you square the numerator and you square the denominator. So this becomes a plus b quantity squared over 2 squared, which is 4. Okay, so we have that portion, and what is left for the variance from the variance equation is this e of x, bless you, quantity squared. Okay, and now remember this is for the uniform distribution. So let's now tackle this e of x squared. Well, if we're talking about the uniform distribution, that's the integral from a to b, and I'm only evaluating between a and b and not from minus infinity to plus infinity because the probability takes on a value of 0 if it's less than a or greater than b. So I only need to care about what happens between a and b. And so I have an x squared, and I have the probability for the uniform, which is 1 over b minus a, the density function. So this is my value, or my expression rather, little x, dx. That's my expression for the variant, for the e of x squared. And I need that e of x squared to complete the variance equation, which I did out longhand to show you that the variance is equal to this expansion. So I look at my expression, and I see this 1 over b minus a. Now remember, my variable that I vary for that integral, vary under the curve, is equal to x. And this 1 upon b minus a does not involve an x anywhere, so it looks like a constant, and therefore I can bring it outside of the integration. So I write 1 upon b minus a, integral a to b of x squared dx. So now I evaluate the indefinite integral. Rather, I use the indefinite integral to evaluate this definite integral. So by the rules of integration, this becomes 1/3 x cubed. So I still have my constant out front, 1 over b minus a. And then I write 1/3 x cubed. And I evaluate that between b and a. Right? So I evaluate this expression at b, and I subtract from it the valuation of that expression at a. So I'm going to write these constants separately, right? 1/3 b minus a. And then I have my expression here for the evaluation of this quantity at b, and I subtract from it the evaluation of this expression at point a for the indefinite integral. Okay. Does everyone understand at this point? Okay, so now if I evaluate it at b, I have x substituted with b, I get b cubed. If I evaluate this at a, I get x evaluated at a, I get a cubed. So the result is, for this e of x squared, that result is equal to 1 over 3 b minus a, and then in the numerator, I have b cubed minus a cubed. Okay, so if I put the two together, this e of x, I find that I get, let me just write it under here, 1/3 b minus a in the denominator, and then I have b cubed minus a cubed. Okay, so I'm almost done, and now what remains is to do a little bit of algebra to combine these two. Okay. So let me go ahead and do that. Now, it is the case that this b cubed minus a cubed is the same as saying, let's say b cubed minus a cubed is the same as saying b minus a times b squared plus ab plus a squared, right? So let's verify that that is the case. So if I multiply b times each one of these terms, that's b cubed plus ab squared plus a squared b. Now, if I multiply the minus a times each of those, I get a minus ab squared, and I get a minus a squared b, and I get a minus a cubed, right? So I'm just multiplying this term times each of that second term, multiplying the minus a times each of those. So here, I have what? I have an a squared b, positive a squared b. I have a negative a squared b. I'm subtracting it from itself. So this term and this term, that's going to go to 0. And then I have an ab squared here, that's positive, and I have an ab squared here, that's positive. So you subtract this from that, that goes to 0. Okay, so now what I'm left with b cubed minus a cubed. And lo and behold, the identity does hold true. So what I can do, any questions about this? So what I can do then is I can replace this b cubed minus a cubed with the factorization of b minus a times quantity b squared plus ab plus a squared. Okay, so let me do that. So I take my 1/3 b minus a in the denominator, that hasn't changed, but the numerator, I'm going to rewrite that as b, brain fart, b minus a times b squared plus ab plus a squared. Okay. So the other term I had was e of x quantity squared, which I have from before, is just minus this a plus b quantity squared over 4. Okay. So let's do a little bit of some. Everyone understand this step so far? So let's do a little bit of simplification. I notice for this term on the left, I have a b minus a in the numerator, and I have a b minus a in the denominator. So that's going to go to 1. And what that leaves me is b squared plus ab plus a squared in the numerator and 3 in the denominator. And then I still have this term, a plus b quantity squared. If I actually do out this square, a plus b times a plus b, that's a squared plus b squared plus 2 times the cross term, 2ab. Okay. Now, I can replace this square with this expansion, a squared plus 2ab plus b squared. So I'm going to do that, and I'm going to rewrite this term here as a squared plus 2ab plus b squared. Okay, and that's over 4. All right, so now I'm going to compute the lowest common denominator here. That's going to be 12. And to get 12 here, I multiply the top by 4 and bottom by 4. So I'm going to get 4 times b squared plus ab plus a squared over 12. And then here, I'm going to get multiply top and bottom by 3 to have the lowest common denominator of 12. So that's 3 times a squared plus 2ab plus b squared, okay, over 12. So I can combine the two. And when I combine the two, that gives me, okay, I have 4b squared plus 4ab plus 4a squared. That's the contribution of this term on the left. And then I have minus 3a squared minus 3 and 2, 6, ab minus, 6ab minus 3b squared. And all of this is over 12. So the first 3 terms is contributed by this factor, multiplication of 4 times that b squared plus ab plus a squared. And the second 3 terms is contributed by this factor on the right here, 3 times the a squared plus 2ab plus b squared. Any questions about this? So we're still doing some algebra, and now we're going to combine terms here. Here we have 4b squared and 3b squared. I'm just going to combine the terms, like terms, just to make it a little bit simpler here. So we have 4b squared minus 3b squared. Okay, those are combined, all right. And then we have, let's look at the AB. We have plus 4AB here, minus 6AB, okay. And then here we have plus 4a squared, and we have minus 3a squared, okay. And this is all over 12. So we combine these, And let me erase up top here so it'll be a little bit easier for those in the back to see what's happening. So 4b squared minus 3b squared, that's just b squared, right? 4ab minus 6ab, that's minus 2ab. And then we have 4a squared minus 3a squared, that's plus a squared. Yes, all over 12. Now, if we take a look at this expression, this is the result of saying b minus a quantity squared over 12. Okay, so that's our result, our expression for the variance. And if we look up there, we have exactly that, the b minus a quantity squared upon 12. Okay, any questions about this? So literally, we're taking the definition for expectation in the continuous case, and we're taking the definition for the expectation for the variance rather in the continuous case, and using the variance equation and doing some algebra to arrive upon these results. Okay. Any questions about this? Make sense? Okay. So that being said, let's move on to the exponential distribution. And the exponential distribution is another continuous distribution, and it's related to the Poisson. And so this is to remind you, we'll call this the Poisson configuration. And as we had studied, the Poisson refers to the number of counts or occurrences of an event in some standard unit of time, delta t. Now, we said the Poisson was probability, discrete probability, because these counts traffic in quantities that are countably infinite, right? There's 0 events, 1 event, 2 events, 3 events, and so forth. So we can draw a one-to-one correspondence with the naturals and the measure of interest for the Poisson. Now, related to these events is the amount of time that occurs between a rare event or rare set of events or between events. And so this idea of what rare means, it means that the rate is relatively small. It doesn't happen very often. And so the happens, I'm getting ahead of myself, doesn't happen very often means that we have a small rate. And what we're concerned about with the exponential distribution, and this example shows a Poisson configuration where the rate is very small. So we only have a very small number of events that occur in each standard window of time, delta t. And so if we were to measure the time between the occurrence of one occurrence of the event and the next occurrence of the event, that distribution that describes this time, the probability of this time, is called an exponential distribution. And so this essentially answers the question of the likelihood that you're going to have to wait a certain number of seconds, milliseconds, or a certain amount of time before you observe the next event. So while the Poisson distribution is a discrete distribution, the related distribution, the exponential, since it traffics in time, the time until you see the next event, it's related, but it's entirely different in terms of the type of the random variable. In the exponential distribution case, it's a real valued quantity, namely time. Okay, so you have a rate, lambda, and it's the same sense of a rate in the Poisson distribution. And this rate is associated with the exponential. And the exponential talks about the probability of how long you're going to have to wait before you see the next occurrence of an event. And this exponential distribution, you'd note that x is distributed as exponential with a rate of lambda. And the density function, it's a density because it's a continuous distribution, time is a real valued quantity, is equal to the following, lambda e to the minus lambda x power. And so it kind of looks a little bit like the Poisson. You have a lambda, you have e to something. But remember, this is a continuous distribution. It's not a discrete distribution. And of course, time, x, is greater than 0. Could be 0.00 something, only marginally greater than 0, but it has to be greater than 0. Okay? All right. Any questions about this? So we're going to take a look at the summary statistics for this exponential distribution. And when you talk about continuous distributions, one of the concerns that you have is this so-called CDF, cumulative density function. distribution function. And remember with the CDF, it's the way you construct complex events. We talk about ranges or intervals of values, and you need the CDF because you need to be able to talk about these quantities that individually, i.e. a single real number, the probability of that single real number is 0 because they're uncountably infinite. So we have an expression here for the CDF. And so what we're going to do is take a moment to derive this expression. And again, we're going to make use of integral calculus. Specifically, we're going to use the indefinite integral to compute the definite integral. And so here we have a definite integral. And there's the contact coordinates for Khan Academy. They have a really wonderful set of modules on the indefinite and the definite integral to jar your memory. Okay, so we have the continuous, the CDF, the cumulative density function. So f of x is equal to the integral from minus infinity to x of the density function f of x dx. And again, for the exponential distribution, for all values that are less than 0, this thing is 0. And so our f of x, our density would be 0. And so we only really care about those portions from 0 to x. So we can take a piecewise approach to this integral, and we write the integral from minus infinity to 0, the density function integrated dx, plus, and we take that portion from 0 to x of the density function dx. So it just happens by the definition of this quantity has this expression for x greater than 0, but for everything that's less than equal to 0, it takes on a value of 0. So this thing is just 0, and all we're really concerned about is that quantity. And so we take this expression and we substitute the density for the exponential distribution. So we write 0 to x of lambda e to the minus lambda x dx. And so we compute the definite integral, and we substitute for value x, and we subtract for that the definite integral substituted for value 0. So if we look at this expression, we see that we have a complex exponent here. We want to simplify this. So we're going to do a substitution and use something called the Jacobian, or maybe you called it U substitution. So we're going to say let U equal minus lambda x. All right, so if U is equal to minus lambda x, not only are we concerned about that substitution, because we're dealing with calculus here, we are concerned about how the substitution changes. So we're also going to compute d dx of this U, which also requires us to compute d dx of that minus lambda x if we're going to make that substitution. Okay, so if we take d du of x, so that gives us du dx is equal to minus lambda. So then we kind of do a little bit of a substitution of some algebra here, and we multiply both sides of equality, as it were, by this dx. So we get du is equal to minus lambda dx, and we multiply both sides by 1 over negative lambda, and we get minus 1 over lambda du is equal to dx. So what does that say? That says if I make that substitution where everywhere I see minus lambda x, I write u, that means everywhere I have a dx, when I substitute that with a du, I also carry this multiplicative factor of minus 1 over lambda. Okay? And so the Jacobian talks about when you make a transformation on something, and so my transformation is taking minus lambda x and rewriting u, you also need to know at what rate does that transformation change. So what does that mean? That says if my x started out as a value of 2, and let's say I increased it to 2.05, at what rate does this u change? And how it changes is by a factor of minus 1 over lambda, right? And the Jacobian is very important in all sorts of disciplines whenever you're dealing with dynamic systems, because if you make a change to something, you need to know how the velocity and acceleration of that thing is modified when you make that change. Okay? All right. Any questions about this so far? Make sense? Okay, so where were we? So we made this U substitution, And so now we write this integral from 0 to x. We had that minus lambda, and we write e to the u du. And because we changed from dx to du, we also have an additional factor, multiplicative factor, of minus 1 over lambda. Okay, so if we do that, well, we have a lambda and a minus 1 over lambda. That changes to minus 1 because the lambdas in the numerator and denominator cancel. And we're left with minus 0 to x, our integral, e to the u du. Okay, so the integral of e to the u is just e to the u. It's actually quite, simple. So we have our result minus e to the u. And so I go back to what my substitution was. It's e to the was minus lambda x, and I'm going to evaluate that at a value x, and it looks weird to say x equals x, but you're just doing substitutions, and I'm going to subtract from it the evaluation for x equals 0. So if I take this, I write, okay, minus this expression evaluated at x and minus this expression evaluated at 0. Okay, so we have evaluation at x. That's minus e to the minus lambda evaluated at x. So it's minus e to the minus lambda x. Okay, I subtract from that this value evaluated where I substitute x with 0. So that's minus e to the minus lambda times 0. Well, e to the 0 exponent is just 1. So that would be minus 1. I have a leading minus sign here, so that would make this a positive 1. So what I'm left with, and let me write that up here, what I'm left with is minus e to the minus lambda x plus 1, or I could rewrite that as 1 minus e to the minus lambda x. And there's my result. So this is the result for the CDF, or the cumulative distribution function, which is needed to construct complex events for continuous distributions. Okay. And we solve for that by taking the definite integral, and we use the indefinite integral and subtract it in order to get our solution. Okay. Any questions about this? Does that make sense? It really would have been much better with the tablet, but it is what it is. All right. So let's move on. And I guess I just did that. All right. So let's take a look at the expectation. And to do the expectation, we're going to make use of integration by parts. And let's recall where integration by parts comes from as a way to remind ourselves about the recipe, if you will, that we use for integration by parts, and why what integration by parts does. So here we have our expectation, and our expectation is just the weighted sum, and in this particular case, we integrate from minus infinity to plus infinity our density function f of x dx. Now, for the exponential distribution, all values less than equal to 0, the f of x, our density function, sorry, I left something out. The value x times the density function, it's the weighted sum, dx. And we use integration because this is a real valued quantity. And so here, our f of x, our density for the exponential distribution, it is 0 for all values of x that are less than or equal to 0. So again, we can rewrite this expression taking that into account, and we have the integral from 0 to infinity of x times our density function f of x dx. Okay, so now we substitute our density for f of x for the exponential distribution, and we get the integral from 0 to infinity of x lambda e to the minus lambda x dx. Okay, and so how we're going to solve this is we're going to solve this using integration by parts. Okay, you've all done integration by parts? Okay, so In integration by parts, it all comes from the product rule or differentiation by parts. And in differentiation by parts, you have a function of the form f of x times g of x. And, an example of that, if our f of x was x squared, our f of x is x, x squared, and our g of x might be, I don't know, 3x cubed, for example, right? So you have some complex function of x, and that complex function of x can be written as the product of two simpler functions of x. Okay, so if we have a function of that form, f of x times g of x, and let's say we wanted to take the derivative, d dx, of this complex function. Okay, so if we do that, the product rule, or differentiation by parts, says that result is f prime of x, the derivative of x, times g of x, plus f of x times the derivative g prime of that g of x function. Okay, so if we do that, we can arrive upon integration by parts. And integration by parts, what we'll find is a method for simplification of the integration of a complex function. And so let's take the integral of both sides of equality, because if you take the integral of this side, you also have to take the integral of the other side. And if you take the integral of the sum of two things, that's the same of taking the integral of each of those and summing together. So we take the integral of d dx of f of x g of x dx, and we take the integral of this dx and the integral of that dx. Okay, so now, of course, the integral with respect to x of d dx is just nothing more than f of x g of x, because the integral is sometimes called the antiderivative. It's sort of the inverse function. Okay, so now we have this f of x g of x, and we have this integral of f prime of x g of x dx, and then we also have this integral of f of x g prime of x dx. Okay, so now let's subtract from both sides of equality this expression here, the integral f prime of x. So we do that, and we have f of x times g of x is equal minus integral of f prime of x g of x dx is equal to the integral of f of x g prime of x dx. Okay, so it doesn't matter which direction you have the equality. You could have this on the right or this on the left. It's the same thing. So if we put this one on the left and the other part on the right, we get this integral of f of x g prime of x dx is equal to f of x times g of x minus integral f prime of x g of x dx. Okay, so what does that say? What that says is that if you have an expression for an integral of the form f of x times g prime of x, and you're taking the integral of that with respect to dx, you can simplify that using the following expansion. You multiply f of x with g of x, and you perform this integral minus f prime of x g of x dx. And so the goal of integration by parts, and let me erase all of this portion. First, any questions about that? No? All right. The goal of integration by parts is simplification. And what does simplification mean? Okay. Simplification means when you do this expansion, you'll notice here, I have this f prime of x. And simplification means that if you choose in the original expression, if you choose your f function and your g prime of x function appropriately, when you do the expansion, it should simplify. And simplify means that a term either goes away or maybe the exponent for that term gets smaller. Okay? So let's take this expression. So the recipe is for integration by parts. Step one, you choose the f of x term. Okay? And then step two, you choose the g prime of x term, and then you use the integral to get what g of x is, g prime of x dx, right? So you choose your f of x term, and then you choose your g prime of x term, and then the third step is you calculate what f prime of x is once you choose your f of x term, and then you calculate what your g of x is by taking the integral of your g prime term that you've chosen. And in this example, we have the following integral. We have 0 to infinity x times, and let's just take that lambda out of it because it's a constant, x times e to the minus lambda x, right? So in this particular example, we have two functions of x. We have x, that's a function, very simple function, and we have e to the minus lambda x. So you're going to choose one of these to be your f of x and the other to be your g prime of x, and then you're going to calculate the other stuff you need and then construct the expansion. Now, if you made a wrong choice, what would happen? Well, let's say we chose this x to be our g prime of x term, and let's say we chose this e to the minus lambda x to be our f of x term. Well, what would happen here? Well, if we took the integral of x, right, that would give us 1/2 x squared, right? It would increase in exponent, right? If we took the f prime for this being the f of x, that would be like -1 over lambda e to the minus lambda x. It doesn't change, right? So this is your key to know you chose the wrong term for your f of x. Now, of course, if we choose the x term as our f of x, and this e to the minus lambda x as our g prime of x term, well, what happens? When we take f prime of x, this is going to go to 1. It's going to go from an exponent of 1 to an exponent of 0. It's going to go away, right? So whenever you're faced with an integration by parts and you want to know which to choose as your f of x term and which to choose as your g prime of x term, your key is, will computing this first derivative of the f of x simplify things? If it doesn't simplify things, you chose wrong. If it does, then you made the right choice. Okay. Any questions about this? Does that make sense? Okay. So now let's choose as our f of x term, let's choose our x. And then for our g prime of x term, let's choose e to the minus lambda x. Okay. So let's carry this through. So we choose f of x. Okay, that's my f of x. Choose g prime of x. So let's calculate f prime of x. So f prime of x is equal to 1. Okay. Our g prime of x is e to the minus lambda x. So that means our g of x is going to be the integral of e to the minus lambda x dx. Now, of course, we can do a u substitution. And if we do the u substitution, we get 1 over lambda minus 1 over lambda e to the minus lambda x, okay, if we do our u substitution, because e to the u, the integral is e to the u. All right, so now we have an expression for our g of x, and we have an expression for f prime of x. Now let's construct this expansion here. So this is equal to, all right, our f of x. F of x is equal to x, right? Our g of x is equal to minus 1 over lambda e to the minus lambda x, okay? And then we say minus the integral of f prime of x, which is just 1, right? So that goes away, it simplifies, times g of x dx. So g of x is minus 1 over lambda. So that's plus 1 over lambda e to the minus lambda x. And that's our g of x. And this is an integral dx. Okay. All right. Any questions about this? Does that make sense? Okay. So now we take this expression and we compute this integral, and that's going to give us the definite integral for this original expression, and then we just use the indefinite integral, evaluating at infinity and evaluating at 0 to get our answer. Okay, so now let's continue on from that, and we're going to take this expression. We have our x times our minus 1 over lambda e to the minus lambda x, and then we have this integral. Let's evaluate the integral. So if we evaluate this integral, let's see. Yeah, all right, this is, let me just clarify. This expansion here is times a lambda because it had lambda times this expansion. So if we take this expansion and we multiply by that lambda, which is what happens here, right? We get rid of this 1 over lambda, and we get x. Actually, no, we can leave that to the end, but yeah, let's leave it to the end. I don't want to confuse things. All right. All right. So we have this expression. Let's just do that integral. We can say let u equal minus lambda x. So then we say du minus 1 over lambda du is equal to dx, right? So we took the ddx of this. We got du dx is equal to minus lambda. You multiply both sides by negative 1 over lambda. Okay, so now this integral becomes the integral of 1 over lambda e to the u du, and then we have another factor of minus 1 over lambda, right? So it's minus 1 over lambda squared. So we have minus 1 over lambda squared. We have our integral e to the u du. Well, that's just e to the u, right? And we substitute back in the u. That gives us back 1 over lambda squared e to the minus lambda x. Okay, so we have this term, we have that term, and we can collect those two together. I'll do that up here. We have x times minus 1 over lambda, so that's like saying minus x over lambda, e to the minus lambda x. And then here we have plus a minus, let's see, did I do that right? Du minus lambda. Did I skip a step here? Let's see, so it's fg. That would be the, if that's g prime, and the first one is something that went weird here. So let me see. So we have f, this was f, this was g prime, and we have g integral of e to the minus lambda x dx. That's minus 1 over lambda e to the minus lambda x. So that's minus 1 over lambda. I had minus 1 over lambda. So that was minus, that's plus. So that's right. So then we did that integral. So that's plus, that's minus. So it'd be minus 1 over lambda squared. Yeah, that's right. Okay. Minus 1 over lambda squared e to the minus lambda x. Okay, there we go. So there's my expression, and I haven't yet multiplied by this leading lambda. It doesn't really matter, but I can do it later after the fact. Okay, so I take this expression and I evaluate it at x equals 0, and I subtract from that evaluation, I evaluate it at x equals infinity, and I subtract from it the evaluation of that expression when x equals 0. Okay, so let's first take a look at x equals infinity. So if I take a look at this expression, I make the observation here, well, I have an x in the numerator, and I have an e to the minus lambda x. E to the minus lambda x is the same as saying 1 over e to the lambda x. So in the numerator, I have x to the 1 power. In the denominator, I have x as our exponent. So if I make x really, really big, well, this increases at a much faster rate than the numerator. So while I have an infinity, if I took the limit, this is going to dominate, the denominator is going to dominate the numerator, and therefore it's going to look like I have 1 over something really, really big, which is 0. So for x equals infinity, because as an exponent, infinity increases much faster than as a regular variable, I can just call that 0, and I'll write minus 0. Does that make sense? Okay, and it's based on limits. So now, for this part of the expression, I have minus, and here that's a negative exponent, right? That's the same as saying 1 over e to the lambda x. Well, I have a constant up here. I have a variable here that's an exponent. I set that to infinity. That's also going to be 0. So I have minus 0 for that term, minus 0 for that second term. So the whole thing evaluates to 0 when I have x equals infinity. So let's take the other part here, our bottom bound of the integral, and I'm going to say what happens when x equals 0. Well, I have 0 in the numerator, okay? That's 0 times something. And of course, this is an exponent, so that's e to the 0 power, which is e to the 1. So I have 0 over something that's non-zero, that's just 0. So I write minus 0. So now this term, well, I have an exponent that's going to be 0. So e to the 0 power is 1. And I have minus 1 over lambda squared. So I'm going to write minus 1 over lambda squared. Okay. So I do that, of course. This is 0 minus 0. That goes to 0. And I have a negative of both things in a negative. That's just 0, so that doesn't count. That goes to 0. So I have minus of something that's minus, which is just plus 1 over lambda squared. Okay. Any questions about that? Now, of course, that was for this expression that's in this bracket. I have a leading multiplied by lambda. So if I have a leading multiplied by lambda, multiply lambda by this, I just get lambda over lambda squared, which is just lambda. All right, so if I multiply by lambda, I get 1 over lambda. Okay, so where does this lead us? Let me check the time. I really wish I had the pen. Yeah, we're almost out of time. I have to figure out why that's not working. Okay, so let me wrap this up since we only have 10 minutes left. So now I get this expression for my, where is it? Integration by parts, 1 over lambda, which is my result. Okay? It really is a lot better to follow with the pen on the tablet, but you know, it is what it is. And so my expression for the expectation of an exponential random variable, I use integration by parts. I use the indefinite integral to solve for the definite integral, and I reduce my expression for the expectation, and I arrive upon the result of 1 over lambda. Okay. Any questions about this? No? Make sense? I do have an old video. It's very poor quality, but what happens when you upgrade in technology, things get better. But unfortunately, in this case, technology has failed us, and it probably still hasn't been able to recognize. Nope, I'm getting 245, room 245 downstairs, and I'm getting three. I'm getting the next room, but I'm not getting this laptop, which is just literally a 1.5 feet away. So I'll try to figure out why that's not working between now. On Tuesday it was working, which you all saw, but for some reason it's not working now. So what we'll do is we'll end there for now, and we'll pick back up on Tuesday with the solution for the variance of an exponential random variable. And what I'll do is when I post this, I'll also post right alongside it the old video where I basically go through all of this in a dark room with a video camera trained on a whiteboard, which is effectively a version of looking at this. Okay. Any questions about this? So please make sure you're reviewing integration by parts as well as reviewing the definite and indefinite integral. because with these continuous distributions, you're going to use it to solve for the expectation and the variance. And once we get through the exponential distribution, we'll look at the gamma distribution and then move on to central limit theorem, and then spend the last 2 or so weeks of class of the semester going over some modeling and introduce the final project. Okay? All right, any questions? The last questions? Make sense? Brings back all that calculus from way back when or whenever. So with that, I'll end there, and I will see you all on Tuesday. Good afternoon. I'd like to continue our discussion on the exponential distribution, continuing on where we left off before the break. And so, where we left off, we talked about this idea of having a period between, or the time that's transpired between relatively rare events. And we motivated that using the Poisson distribution. So to draw your memory, we have a set of events that we observe in time over modules of observation delta t. And the only requirement, as we had discussed, was that each of the delta t's should be the same. So delta t could be a second, could be 10 seconds, could be a minute, could be 15 minutes, could be an hour, what have you. And so the idea then that we talked about Poisson was with the number of events that we observe in a module of observation. But here we're talking about the time that has elapsed, or the time before we see the next event. So, for example, in this first module of observation delta t, we observe an event here depicted by that circle, and then sometime later we see another event, and so we might want to know what is the time that's transpired, marked by this green arrow, until we observe the next event. And as we discussed, that measurement, if you will, time, the probability of a certain amount of time before we see the next event, that is an uncountably infinite quantity, and therefore we use a continuous distribution. And as we had discussed, the continuous distribution has a density function, and the density function is nothing more than the derivative of the cumulative distribution function, or CDF. So we have PDFs, or probability density functions, for continuous distributions that measure or traffic in uncountably infinite quantities. Okay, and so this is the exponential distribution. Notationally, we write x, our random variable, is distributed as, that's what this tilde corresponds to notationally, as an exponential, and this exponential distribution is parameterized by lambda, where lambda is a rate parameter. And so we said the density function is as follows: f of x, the probability density function, so it's density because time is uncountably infinite, it's real value. F of x is equal to lambda e exponentiated to the minus lambda x. Now, of course, you can talk about zero time, right? But typically when we talk about the exponential distribution, we talk about time being positive, right? Time can never be negative, and nothing time doesn't exist, right? It can be very, very small, very close to zero, but it's greater than zero. Okay, so let's take a look at this cumulative distribution function, or CDF, for the exponential distribution. And from before, whenever we talk about any distribution, we need to discuss or develop or derive, if you will, various points such as the summary statistics. We look at the law of total probability and prove that. We prove the mean, and we prove the variance. Now, for our continuous distributions, like exponential distribution, that traffic in real valued quantities, it's important to derive the CDF, the cumulative distribution function. Okay, so here, when we think about the exponential distribution, the CDF, as we talked about, our CDF, that was symbol F, and we said that was equal to probability minus infinity up to some value x of the density function, dx. Now, of course, if we take a look at the exponential distribution, we said it's only defined for x greater than 0. So that means if we were to plot out a graph of the exponential distribution, this is minus infinity, this is x
and this is 0, well, it's going to be 0 until it's just past our x, our x equals 0, right? And so because it's 0 everywhere here up to and before, including the 0, we just rewrite that CDF, that expression for the CDF, as being equal to 0 plus the integral from 0 to x of f of x dx, or of course, for this f of x, we're going to substitute in the density function for the exponential distribution. Okay, so in order to do that, we're going to make use of calculus. Specifically, in this case, we're going to make use of the definite integral, right? So please make sure, and I have a URL there on something like Khan Academy or the equivalent, please make sure that you're reviewing the definite and the indefinite integral, okay? So let's take a look briefly at that definite versus indefinite integral, right? So it all comes from something called the fundamental theorem of calculus, to jar your memory, because you should have calculus as a prerequisite for this class. The fundamental theorem of calculus states the relationship between the definite and the indefinite integral, okay? And so what does it state? It says, if I want to compute the integral between some lower bound and upper bound of a function, f of x dx, that's equal to, right, that's called the definite integral. The definite integral is equal to the antiderivative or the indefinite integral at the upper bound, and you subtract from that the antiderivative at the lower bound. So essentially what it's saying, to compute the definite integral between 2 points, A and B, we take the antiderivative at the upper bound and we subtract from that the antiderivative at the lower bound. Okay? And so one observation to make is this looks a lot like the CDF, right? It looks a lot like the CDF, and in fact, if you think about it, the CDF is the antiderivative of the PDF, where antiderivative of some function f is a function, we're going to call it capital F, such that the derivative of capital F is equal to the original function little f. Okay, so that's our definition of the antiderivative. And the fundamental theorem of calculus says, basically, if we want to take the definite integral, right, meaning between two boundaries, we subtract the indefinite integral at the upper bound. We take that and we subtract from it the indefinite integral at the lower bound, also known as the antiderivative. Okay, so let's erase this and continue on, given this definition. So we have a rare event in time. And given this rare event, we said that the probability of describing the amount of time before you see an event or between events is governed by this exponential distribution. And we said that the density function, f of x, is lambda e exponentiated to the minus lambda x, and it's defined for all x or times greater than 0. So if we were going to compute the CDF, right, we take the definite integral, of course the integral from minus infinity up to x, that's the CDF, right? We can apply the fundamental theorem of calculus to compute the definite integral. So let's do that. So here, we plug in the integral, everything else is 0, from 0 to x of f of x, which is the density function, the PDF, probability density function, for the exponential distribution, dx. So we plug in our density function, lambda e to the minus lambda x power, plug that in for f of x, and we write the following expression. Okay, so let's begin from there and actually apply that fundamental theorem of calculus in order to compute the definite integral. So we start out, and we have the integral from 0 to x of lambda e to the minus lambda x dx. Okay, so we take a look at this, and we observe, okay, well, this factor here, lambda, it does not involve x, so we can certainly treat it like a constant underneath this integration. So we can pull that out and write lambda integral 0 to x of e to the minus lambda x dx. So now we're going to make a substitution. We're going to do something called the Jacobian, right? Taking the integral of this expression, e to the minus lambda x dx, is kind of difficult because we have a complex expression there for the exponent of the e. So we're going to make a substitution. So we're going to say let u equal minus lambda x. Okay, so if u is equal to minus lambda x, and we took the derivative of this u, right, because we're interested not only in the substitution, but if this thing changes, how does this substitution change under the derivative, right? So we're going to write dx of this u is equal to dx of this minus lambda x. Okay, so we do that, and on the right-hand side, we just get minus lambda, because ddx of x is just x to the 1 power, x goes to 0, and we get minus lambda, and we have a du dx over here. So now we do a little bit of algebra, and we write du is equal to minus lambda dx. So that means every time we have a change in u, that's a factor of minus lambda for the change, requisite change in x. Okay, so we can do some algebra here. We divide both sides of equality by minus lambda, so we get minus 1 upon lambda du is equal to dx. Okay, so you'll notice here, when we take the integral, this is saying the area under the curve for a very small increment. Remember what the integral corresponds to. The integral corresponds to the area under the curve by taking very small slivers of x, infinitesimally small, to make a rectangle. The height of this rectangle, that's our f of x. The width is our delta x, or dx. So the area of this little rectangle is f of x dx. So we add those rectangles up over some interval, right? And that gives us our area under the curve, all right? The Riemannian sum. Okay, so what does this mean? This means that every time here I see a dx, that's a change. Every time I see a dx, if I want to substitute with a du, there's a scalar factor that I have to incorporate. Okay, so let's do that. Let's apply this. So I say, I want to simplify this, so I'm going to call it, instead of e to the minus lambda x, I'm going to call it e to the u. But if I do that, my dx has to change. If I change it to du, it also changes by a factor of minus 1 upon lambda. So I have my original lambda out front of the integral between 0 and x. I write a minus 1 upon lambda e to the u du. Okay, so let's do a little bit of algebra. And if we do that, we see that, of course, I have a 1 upon lambda, I have a lambda, a minus sign, that's just equal to minus 1, 0 to x, and I have e to the u du. Okay, so the integral of e to the u du, that's just e to the u, right? So our result from that is just minus, because we have that minus sign, e to the u. Okay, so we're going to now take our indefinite integral and we turn it to a definite integral by evaluating the indefinite integral at both ends, the upper bound of this integration minus the lower bound. So we say minus e to the u, and then we're going to go back to our substitution and replace u with minus lambda x. That's our result. And we evaluate it at x at the upper bound and 0 at the lower bound. So we're going to say we take this indefinite integral, which is the indefinite integral of this expression, and we evaluate at the upper bound x, and then we subtract from that the indefinite integral evaluated at the lower bound. Okay, so let's do that. So if evaluate, it just so happens that this x is the same, but we're still going to substitute everywhere we see the variable here. We're going to substitute this value, right? I could have said e to the t and just substitute x as t. Doesn't matter. They're just dummy variables. So that's minus e to the minus lambda, substitute x, minus e to the minus lambda x, minus, substitute 0 in this x, a minus e to the minus lambda times 0, right? Okay, so that makes it e to the 0 power. Anything to the 0 power is 1, and we get minus e to the minus lambda x plus 1, okay? Which is the same as 1 minus e to the minus lambda x, okay? And there's our result. Rather 1 minus e to the minus lambda x. So the CDF, or the cumulative distribution function, for the exponential distribution is 1 minus e to the minus lambda x power. And there's our result. Okay, so now that we have our CDF, now we can proceed with other things for this exponential distribution. We'll move on to computing the mean as well as the variance of this exponential distribution. Let's see how the camera's doing. Okay. All right. So let's move to the variant, the mean rather, and we have, of course, our PDF, probability density function, for the exponential distribution. And again, that PDF, or probability density function, is f of x, is lambda e to the minus lambda x power. And we just solved for the CDF, cumulative distribution function, using the fundamental theorem of calculus. And we have capital F of x, the CDF, is 1 minus e to the minus lambda x. Now, of course, as a kind of segue, if you take the derivative of capital F of x, that's exactly the PDF, right? You can do that for yourself. Prove it to yourself. The CDF is the antiderivative of the PDF, okay? All right, so let's look at expectation. Now, of course, when we talked about discrete distributions, we said the expectation is the probabilistic average for each value multiplied by the probability for which that value occurs. Now, because we're dealing with continuous distribution trafficking in real value, uncountably infinite quantities like time in this example, we replace the summation from before when we had our expectation with the integral. So again, of course, when you take the expectation, that expectation for the mean of a continuous variable is from minus infinity to plus infinity. And we just got done saying x times f of x dx, right? That's our expectation. But for the exponential distribution, for all x's greater than 0, we said that it's undefined. It's actually 0. So that means we can break this up to e of x equals, going from minus infinity to 0, x times f of x dx, plus, from 0 to positive infinity, x times f of x dx. And of course, since the value of our density is 0 during these boundaries, this term goes to 0, leaving us with the following expression for the expectation. Okay? All right. So let's erase this. And we want to reduce this expression. But this expression is kind of complex, right? It doesn't afford us any ability really to reduce it. So we're going to make use of integration by parts in order to simplify this expression. And of course, certainly, here's a URL to Khan Academy. There are other such sources. Please review, refresh your memory on integration by parts. Okay. So let's take a segue briefly, and we'll just go over where integration by parts comes from, and then we'll apply integration by parts in order to solve what the expectation is for the exponential distribution. Okay? All right. So let's take a look at integration by parts. So recall, if you will, when we talked about derivatives, or when you had derivatives in calculus, there are some expressions that are of the form f of x times g of x. Okay. And of course, an example might be, x times e to the x, right? This might be, for example, your f of x term, and you designate this function as your g of x term, right? So recall, when you take a derivative, you had derivation by parts, or derivative by parts. And derivative by parts was a prescription, if you will, for solving derivatives of functions, complex functions, that can be expressed in this form as a product of two, simpler function or product of two functions. So let's take this expression, and let's take you back to derivative by parts, and I want to compute dx of this f of x times g of x. So we said, okay, we take the first thing, derivative times the second thing, and then plus the first thing times the derivative of the second thing, okay? So let's write that out. That's equal to f prime of x, the derivative of f, times g of x, plus f of x times the first derivative of g, or g prime of x. Okay, so now let's turn this into integration by parts. It's absolutely related to derivative or derivation by parts, derivative by parts. So let's take the integral of both sides of equality. So everything you do this side, you do to that side. So we're going to take the integral of this dx of f of x times g of x, that multiplication of two functions, and we're going to take the integral of everything here, this term plus that term. Now, of course, for an integral, recall from calculus that the integration of a sum is the sum of the integrals, right? So we can write this, if I take the integral of this whole expression, that's the same as the integral of the first thing, f prime of x times g of x dx, you can't forget the dx, plus the integral of f of x g prime of x dx. Well, it looks like a t, dx. Okay. So now, of course, let's do a little bit of simplification. If we take the integral of the derivative, what's that? That's exactly just the function itself, right? Because the integral of the derivative of a function gives you back the function itself. So we're going to write f of x times g of x here, and then still we have what's on the right-hand side of equality, which is just f prime of x, g of x dx. You get the chair here, plus integral of f of x, g prime of x dx. Okay, so now I want to isolate this part of the expression, that term, right? So I'm going to subtract from both sides of equality the other term here, right? So I get f of x times g of x minus the integral f prime of x g of x dx is equal to the integral of f of x g prime of x dx. Now, of course, for equality, it doesn't matter which thing is on the left-hand side, which thing is on the right-hand side. So I'm just going to reverse everything on the right-hand side of equality. I'm going to put on this side. Everything on the left-hand side of equality, I'm going to put on your right-hand side. So let's do that. And we're left with the integral of f of x g prime of x dx is equal to f of x times g of x minus the integral of f prime of x g of x dx. Okay, so what does this give us? What this gives us is a prescription for simplification of a complex integral. It says that if I have an expression of the form, the integral of f of x g prime of x dx is equal to f of x times g of x minus the integral of f prime of x g of x dx. And if I choose which of my functions in the original expression is the f of x term and which in my original expression is the g prime of x term, if I choose them correctly, or choose them wisely, if you will, I can get an expression that's simplified, right? So what do I mean by that? So when I say it's simplified, I mean that when you take an expression of this form and reduce it to that form, it actually gets easier to solve, right? So what does easier to solve mean? Easier to solve means that an exponent decreases or a term goes away, right? So what are the steps you need when you're doing integration by parts? Well, step one, you choose the f of x, right? So remember when I said an example of f of x times g of x is x times e to the x, right? And I have two choices. I could either choose this as my f of x and that as my g prime of x, right? So if I did that and say I had an integral involving these, right? I choose one of them, if I had an integral dx, I choose one of them to be the f of x term, one to be the g prime of x term. I could choose this one, the second one, e of x, to be the f of x term, and choose that one to be the g prime of x term. Now, of course, if I choose wisely which of these two, in this multiplication of two functions, which of those two is the f term, you'll notice here when I do this expansion, I have an f prime. So if I choose the f term such that when I take f prime, it simplifies, that's going to make it easier for me through this equivalence, through this reduction, okay? All right, so if I chose the f of x term to be this first term here, the x, if that's my f of x, then my f prime of x is going to be equal to 1, right? It goes away, it simplifies. So let's write down a scheme for how we're going to do this integration by parts. And it comes from differentiation by parts. So step one, we choose the f of x, right? So we have an integral expression of this form. We choose which term is the f of x term. Then step two, we choose the g prime of x term, right? Then step three, we calculate, or compute, I should say. No, calculate's right, calculate f prime of x, right? The derivative of the f of x term. And then four, we calculate the g of x term, which is nothing more than the integral of the g prime of x dx, right? So we compute g of x by taking the integral dx of that g prime of x term. Okay? All right. So let's do this, and we're going to do this with the exponential distribution and use it to compute the expectation, and then we're going to use it again to compute the variance of the exponential distribution. Okay. So let's erase all of this and continue forward with our derivation of the expectation for our exponential distribution. So we have our exponential distribution. Again, we have our density function, f of x is equal to lambda e to the minus lambda x. It's defined, or non-zero rather, for all x greater than 0, or all times greater than 0. From before, we had the cumulative distribution function, or CDF. That's capital F of x is 1 minus e to the minus lambda x. We did that using the definite integral. And here we have an expression for the expectation, and it's an integral where 0 is on the lower bound of the integration because it's the whole expression is 0 when it's negative x is less than 0, and the upper end or the upper bound of this integral, it's a definite integral, is infinity. And so, like in expectation, we have the value x times the probability of x dx, right? It's a probabilistic average using the integral. Okay, so we have our x. We're going to substitute the PDF, probability density function, f of x, in this expression. And so we have, we're making that substitution, we have x lambda e to the minus lambda x dx integral from 0 on the lower bound up to infinity, positive infinity, on the upper bound. Okay, so let's do that. So again, let me remind you of the steps. Step 1, you choose your f of x term. 2, you choose your g prime of x. And then 3, you compute f prime of x. And then 4, compute or calculate your g of x, which is just the integral of g prime of x dx. Okay, so let's try this out. So here we have e of x is equal to the integral from 0 to infinity of x lambda e to the minus lambda x dx. So if I chose the e to the minus lambda e to the minus lambda x, right? If I chose that as my f of x, and I take the derivative, that's not going to make it any simpler, right? So that's the wrong choice. And if you're ever at a loss to figure out which should I choose as my f of x term and which should I choose as my g prime of x term, try it both ways, but you should always think first to choose your f of x term such that when you apply the integration by parts, it'll get simpler, right? Because remember, integration by parts is f of x times g of x minus the integral of f prime of x g of x dx. So that's going to be the reason why it gets simpler, right? Okay, so if we look at that, we have two terms. We have our x to the 1 power, and we have lambda e to the minus lambda x term. So I'm going to choose this x term to be my f of x, right? And I'm going to choose this lambda e to the minus lambda x to be my g prime of x. And the reason for choosing this x as my f of x is because when I compute f prime of x, take that first derivative, this is going to go away, right? It's going to be simpler. So let's do that. So choose my f of x, all right, that's my x. Choose my g prime of x, that's my lambda e to the minus lambda x power. So now I'm going to take step 3 rather, and I'm going to compute my f prime of x. So step 3 says compute. So d dx of, or rather, f prime of x is equal to, right, what's the first derivative of x? That's just 1. Okay. Now, step 4, I have my g prime of x is equal to lambda e to the minus lambda x. So that means g of x is equal to my g prime of x integrate. So that's g prime of x is lambda e to the minus lambda x dx. Okay. So if I do that, I look at this, and I notice this integral is kind of hard to carry out. So I'm going to make a substitution, right? I'm going to say let u equal minus lambda x. So du is equal to minus lambda dx. So that means minus 1 over lambda du is equal to dx, right? So I'm going to make that u substitution. And if I do that, I'm going to get my integral, so g of x, is equal to my integral of lambda times minus 1 over lambda e to the u du. Okay, because I'm going to replace here a 1 over lambda with the du. If I want to switch from dx to du, I have a factor of 1 over lambda. And so my exponent here changes based on my substitution with this u. Okay, so, all right, so let's do a little bit of algebra here. That's the integral of minus e to the u du. That's just equal to e to the u. That's the indefinite integral of e to the u du. And I have that leading minus sign. Okay, so this is my, and I can make that substitution back, minus e to the, what's our substitution? Minus lambda x, right? So that's my g of x. My g of x is minus e to the minus lambda x power. Okay, so I have my f of x term, that's x. I have my g of x term, I compute it, step 4, that's minus e to the minus lambda x. I have my f of x, I have my f prime of x, that's 1. And I have my g prime of x, which is just lambda e to the minus lambda x. So let me go back to my definition that I derived from integration by parts. And I'm going to set up this expression that says my integral from 0 to infinity of f of x, that's x, g prime of x, that's lambda e to the minus lambda x dx, lambda x dx, should be a lambda, okay, is equal to, so I say f of x times g of x, so that's x. G of x is minus e to the minus lambda x, minus e to the minus lambda x, okay, minus, right, so that's my f of x times g of x, minus the integral of f prime of x, that's 1, times g of x, that's minus e to the minus lambda x dx. Okay, so I do that. I'm going to erase some of this so we have more room on the board. We do that, and let's do some simplification here. That's equal to, we have a minus x e to the minus lambda x, and then we have here a minus, let's see, so that's minus 1, so that's plus integral of e to the minus lambda x dx. Okay, so, between 0 and infinity, okay, because that doesn't change, 0 and infinity. There we go. All right. Oh, no, I'm sorry. That's wrong. So, now we have this integral, it's simplified, right? Because the x term went away. It went to 1 because of the first derivative of our f of x. And we're going to look at this expression. We're going to do a u substitution. If we do a u substitution, we get a factor of minus 1 over lambda, right? So, essentially, you're doing a u substitution and I'll leave that to you to do. Let's just write the next step. Minus x e to the minus lambda x, right? So then we have a minus 1 over lambda e to the minus lambda x, okay? Because that is the indefinite integral of e to the minus lambda x. Okay, so we have this expression, and now we're going to take this indefinite integral that we solved by integration by parts, and we're going to evaluate it at the lower bound 0, upper bound is infinity, and we're going to take the indefinite integral evaluated at the upper bound, subtract from it the indefinite integral evaluated at the lower bound. Okay, so one of the things you'll notice here, let's take a look first at the upper bound, look at that evaluation. One of the things you notice is that these exponents are all negative, right? And this term, the minus xe to the minus lambda x, if you were to write that out, that's equal to, let me rewrite it up here so you can see, equal to minus x e to the minus lambda x minus 1 over lambda e to the minus lambda x evaluated at infinity, subtract evaluation at 0. Okay, so let's erase this other stuff, and we'll continue on from the board over here. All right, so one thing to look at, if we look at this first term here, that's minus x over e to the lambda x power. Now, if we evaluate this setting x to infinity, well, we have infinity in the numerator. That might seem very daunting, but if we look in the denominator here, we have x as an exponent. So an exponent increases much faster than just a value x, right? So this is going to increase much, much faster than this, and as infinity, gets very, very big, or x gets very, very big, this is going to go to 0, right? So we can write for this term, evaluated at infinity, we can write a minus 0, because this is 0. Now this term, right, that's a minus exponent, that's a constant, 1 over lambda. So this is also going to be 0, because this is a minus exponent. It's going to be a very large negative exponent. That's going to be minus 0, minus 0, right? So that's evaluated at infinity. So we're going to subtract from that this same expression evaluated at 0. Okay, so we know that 0 times anything is 0, right? So that's going to be minus 0. And then we're going to say minus 1 over lambda times e to the 0 power, because that would be a 0 exponent, is 1. So that's minus 1 over lambda. So we have evaluated at 0, right? So this is the term for this indefinite integral evaluated at infinity. And then in this square bracket is this indefinite integral evaluated at 0. And that's how we get the definite integral. Okay, so we have this term is 0 minus a minus, all right, that's plus 1 over lambda. Well, 0 plus 1 over lambda is just 1 over lambda. Okay, and that's our result. So here, with our integration by parts, we're going to use that to reduce or simplify this complex expression for the expectation. All right, this is the expression for the expectation, but we can tease this apart as the product of two functions. We chose the x term as our f of x, and we choose the lambda e to the minus lambda x as our g prime of x, and then we perform integration by parts as usual. Okay, so this is our expression for the expectation that we arrive upon using integration by parts. Okay, so let's write that result for our expectation. So now we have our PDF, probability density function. F of x is lambda e to the minus lambda x power. We have our CDF, the antiderivative, if you will, of the PDF, our cumulative distribution function, capital F of x, 1 minus e to the minus lambda x that we arrived upon using the definite integral. And then we computed the expectation that we arrived upon using integration by parts. Okay, and then we used some u substitution or the Jacobian along the way. So now, let's look at the variance. And to solve the variance for the exponential distribution, we're going to make use of the variance equation. And the variance equation says the variance of x, so sigma squared is the Greek symbol for the variance. Variance of x is equal to e of x squared. So you're going to take your x and you square it and take its expectation, minus e of x, which we just solved for, 1 over lambda, and you're going to square that result for the expectation. Okay? So the expectation of x squared minus the square of the expectation that we just solved for, the square of the mean. Okay. So let's write that out. So here in this second term here, we just substitute what we solved for e of x. That's 1 upon lambda quantity squared. So 1 upon lambda quantity squared. If we were to take this and we were to square it, that's equal to 1 over lambda squared, right? So we get this minus lambda squared here, right? So we're all set with that term. So what remains now is to take the expectation of x squared. So again, it's the probabilistic average, and this is only defined for x greater than 0. So because it's for x greater than 0, we have an integral from 0 to infinity, right? And we have the value here, x squared, there's our x squared, times the the density function. So it's a probabilistic average. So we have x squared times f of x. So the f of x here is our PDF, our probability density function. F of x equals lambda e to the minus lambda x power. So we have this part here is all taken care of. Now what remains is to compute this part. So we have this integral from 0 to infinity of x squared lambda e to the minus lambda x dx. And that's a complex function. And so the question we ask ourselves is, how are we going to reduce this? Certainly, we're going to use integration by parts. So let's do this integration by parts. And when we see this function, we're going to treat this term as our f of x, right? And we're going to treat this term as our g prime of x, right? And as we said before, the reason for that is that when we compute the f prime of x, this x squared is going to simplify. It's going to simplify to 2x. But what we'll find is that we're going to have to run integration by parts twice to get this ultimately to simplify. Okay, so let's do that. So again, step 1 in integration by parts, we're going to choose our f of x. All right, we did that. F of x is x squared. X squared. We're going to choose our g prime of x. That's our lambda e to the minus lambda x. So now we're going to compute our f prime of x. We get a better marker. That's just 2x, right? This is the derivative of x squared. And then the fourth step, we're going to compute our g of x, which is just the integral of lambda e to the minus lambda x dx. Now, of course, we can make a u substitution here. If we let u equal minus lambda x, we get minus 1 over lambda du. It's 1 over lambda. Minus 1 over lambda du is equal to dx. So if we do this integral, we get equal to, we have lambda times minus 1 over lambda integral of e to the u du, right? That's nothing more than minus e to the u, which is the same as minus e to the minus lambda x. Okay, so that's our g of x. Our g of x is minus e to the minus lambda x, and our f prime of x is 2x. Our g prime of x is lambda e to the minus lambda x, and our f of x is x squared. Okay, so here we're going to do this reduction, and we're going to write out what our integration by parts is using this prescription that we solve for our integration by parts. Okay, so let's do that down here. So we start out, we say this expression is equal to, and we said f of x times g of x. So our f of x is x squared, so x squared. Our g of x, we just said, was minus e to the minus lambda x. So times minus e to the minus lambda x. So that's f of x times g of x minus the integral of f prime of x. That's 2x. That's f prime of x. G of x dx. So g of x is minus e to the minus lambda x. So that's a minus e to the minus lambda x. So that's e to the minus lambda x. Minus times minus, that's plus, dx. So as we can see, this has already gotten a little bit simpler. But it's not simple enough. We want to take this expression, and we're going to simplify that expression, again, with a second application of integration by parts. So with the second application of integration by parts, we're going to let this term be our f of x, and then we're going to let this term be our g prime of x. So if this is our f of x, our f prime of x is going to equal to 2. Okay, that's good. And if this is g prime of x, our g of x is just going to be the integral of e to the minus lambda x dx. Okay, so this e to the minus lambda x dx, we could do a u substitution, and that's just equal to, after it's all said and done, minus 1 over lambda e to the minus lambda x. Okay, all right. So if we're going to now reduce this term, right, let's write out the second application of integration by parts. So let's go up here, and from before, let's just kind of block that off. We're going to take this term, keep the first term, but expand this using integration by parts. So we have, give us lots of space, x squared, let's say, minus x squared e to the minus lambda x plus, okay, so f of x times g of x, that's our prescription up there for integration by parts. So f of x is 2x plus 2x, and our g of x here times minus 1 over lambda e to the minus lambda x, right? That's g of x minus, because it's f of x, g of x, minus the integral f prime of x is just 2, and g of x is again 1 over lambda e to the minus lambda x dx, and it's a minus 1 over lambda, so it's a plus. Okay, so I look at this integral, and I can actually solve that, right, with the u substitution. So that would be 2 over lambda times minus 1 over lambda e to the minus lambda x, right, which is equal to minus 2 over lambda squared e to the minus lambda x. Okay, so this is my expression from before, the first time I unrolled, if you will, integration by parts. I ended up with this expression. and then I applied integration by parts a second time on this integral term, and I get this expression, right? So let me write that over here, right? Actually, let me write it. Yeah, I'll write it here. So we have resulting. We have minus x squared e to the minus lambda x plus 2x over, and we'll carry out that minus sign, minus 2x over lambda e to the minus lambda x. And then I have that last term, minus 2 over lambda squared e to the minus lambda x, right? So that's minus x squared e to the minus lambda x minus 2x over lambda e to the minus lambda x minus 2 over lambda squared e to the minus lambda x. Okay, so we take this expression, and this expression is the indefinite integral of this term, integral 0 to infinity of x squared lambda e to the minus lambda x dx. But we're not done, because remember, the fundamental theorem of calculus says that in order to evaluate the definite integral between the boundaries 0 and infinity, right, the lower bound and upper bound, we have to subtract, right? So we have this expression, minus x squared e to the minus lambda x minus 2 over lambda x e to the minus lambda x minus 2 upon lambda squared e to the minus lambda x. I'm going to take this whole expression, and I'm going to evaluate it substituting at x equals infinity. And for x, I'm going to subtract from that same expression evaluated at x equals 0. Okay, so let's make an observation here. So here, let's start with evaluation of this expression at infinity, right? So let's write infinity below that. And one of the observations we make for this term, well, we have an x squared, but we have e to the minus lambda x. So that's like saying minus x squared over e to the lambda x. If I substitute infinity everywhere I see x for that first term, well, I have an x squared term, right? Ooh, that gets pretty big. But here, I have x in the exponent here in the denominator. That increases a lot faster when you exponentiate to the x versus just saying x squared. So if I make x really big, i.e. infinite or approach infinity, this is going to be so much larger than this, it's effectively 0, right? So this term goes to 0. So I'm going to write minus 0 for that term. Let's do the same thing here. Same thing happens, right? I have a 2x over lambda e to the lambda x power, right? So the denominator here, if I look at it, that has x in the exponent. That's going to increase a lot faster than this x. So if I set x to infinity, this is going to be effectively 0, okay? So same deal. This goes to 0. So for this term, second term here, I'm going to write minus 0. Okay. So for the third term here, well, this minus 2 over lambda squared, that's a constant, right? So it doesn't matter too much. But we have here a negative exponent with an x. I set x equal to 0, or x gets really big. That's going to go to 0 as well. So I write minus 0. Okay. So we evaluate this expression for the indefinite integral of x squared lambda e to the minus lambda x dx integrated from 0 to infinity. We evaluate this indefinite integral at infinity, and then we're going to subtract from it that same indefinite integral evaluated at 0. Okay, so now let's do the 0 case. So let's look at the first term. We have x squared, right? 0 squared is 0, and 0 times anything, it doesn't matter what that is 0. So we're going to write 0 for that first term, minus 0, just to kind of be consistent. All right, sorry, minus 0. Let's look at the second term. The second term, we have minus 2 over lambda x e to the minus lambda x, right? We have an x there set to 0. That makes this term 0. 0 times anything is always 0. So that term is going to be 0. So we'll write a minus 0 here. And now let's look at the third term here. So we have a minus 2 over lambda squared, e to the minus lambda x, set x to 0. The exponent becomes 0. E to the 0 power is 1, or anything to the 0 power is 1. So that's minus 2 over lambda squared. Okay, so now we simplify this, and we have 0 minus a minus 2 over lambda squared. That's plus 2 over lambda squared, which is equal to 2 over lambda squared. Okay, so we get the evaluation of the definite integral for this e of x squared, which is just this term, this integral from 0 to infinity of x squared lambda e to the minus lambda x dx. That is equal to 2 over lambda squared, right? So let's erase all that, and that's 2 over lambda squared. All right, so let's write that in. So we just said this integral is 2 over lambda squared. So we have here, for e of x squared, that's 2 over lambda squared minus 1 over lambda quantity squared, right? Because of the variance equation. So that's nothing more, if we were to simplify this, that is, let me write that 2 a little bit better, that is 2 over lambda squared minus 1 over lambda squared. Okay, so 2 over lambda squared minus 1 over lambda squared, that's nothing more than just 1 over lambda squared, right? So we get the variance of x for an exponentially distributed random variable is equal to 1 over lambda squared, okay? So we simplified that by using the variance equation, and from the variance equation, we substitute in what we got before for the expectation, and then we set out to solve this first part, which was e of x squared. We substituted in, so we got x squared lambda e to the minus lambda x dx, and we did integration by parts 2 times and got a result which we then substituted back into the variance equation, and there's our answer. Okay, so again, we got this result, 2 over lambda squared, by running integration by parts twice on this first term corresponding to e of x squared from the variance equation. And then we plugged in expectation, took the square of the expectation for a second part, and we get 1 over lambda squared. So with this integration by parts, you can apply it, or unroll it if you will, as many times as you need in order to simplify your expression. Okay. So that's all I had for today. And please make sure that you're reviewing a number of things. And when you review these things, don't just passively watch them. Actually get a pencil and a paper and do them. Be active in the practice, not just watch someone else do it. And so make sure you are reviewing, of course you should have reviewed by now Taylor and Maclaurin series, and there's a URL from Khan Academy. Make sure you're reviewing the Indefinite and Definite Integral, some excellent modules in Khan Academy. Those aren't the only sources, but those are the ones I'm recommending you consult. And then lastly, make sure you review integration by parts and you become conversant with that. So that's all I had for today. I will see you on Wednesday.